Welcome to class of physics. In previous video we have studied the collisions, so that is elastic collision and inelastic collision under the condition of constant masses. So they were studied on the basis of conservation of momentum. Okay, so that is for conservation of momentum of constant mass. There we have not changed any masses, or there is no variable of masses. But in this class we are going to study the conservation of linear momentum in case of variable masses. Conservation of linear momentum in case of variable masses. So that is one of the best example for that is a rocket. Okay, here first we are studying only about single stage rocket. So rocket means it works on the principle of conservation of momentum under variable masses. Till now you know that the principle of rocket is Newton's the law of motion. There is equal and opposite reactions. Okay, so that means the rocket follows the motion under the principle of Newton's the law of motions, and its actual principle is conservation of momentum under variable masses. So rocket is a device which is used to place the satellite into an orbit. Okay, a rocket carries both the fuel and oxidizer which burn in combustion chamber within the rocket. When the rocket is fired, the exhaust gases rushes downward at high speed and pushes the rocket upward. Thus, the thrust on the rocket is supplied by the reaction forces of the high speed gases ejected at the rear. Okay, let's discuss. So this is a rocket. It consists of fuel and oxidizer. Okay, so these tanks are fuel and oxidizer tanks, and there is a turbine is their engine. Okay, and here this is valves through which the exhaust gas is coming outwards, and so here the firing chamber is there. Here we are not studying the parts of the rocket, just we are going to study the motion of rocket or equation of rocket. Let's come to the definition of rocket. It is conservation of linear momentum. Okay, what is conservation of momentum? The momentum is remains constant. If there is a action, that means before action and after action the momentum is same, remains constant. So it is a device used to place the satellite into an orbit. Okay, so it is a device or it is a vehicle which place the satellite into an orbit. Rocket carries both the fuel and oxidizer. The major mass of the rocket is from the fuel and oxidizer. Okay, so major masses are from fuel and oxidizer. And also it have at its one end instruments, that is satellites, which burns in combustion chamber within the rocket. Okay, whatever the fuel and oxidizer is there, so that is burns within the rocket only. When the rocket is fired, the exhausted gas rushes downward. Okay, when rocket starts, it starts exhausting the gas outward from this valve at high speed, and rocket pushes upward. So here it is a Newton's third law of motion. When gas is outwards, the rocket pushes upward. Thus thrust on the rocket is supplied by the reaction forces. Thrust means it is a force that is supplied by the exhausted gases. Okay, how it works? Okay, how the conservation is here? Let's see. Here is the case. Okay, once again here one more definition is there. Rocket consists essentially of an engine fuel. It is the job of engine to burn the fuel and throw the products out the end of the rocket. The operation of rocket is an excellent example of law of conservation of momentum. Okay, here rockets are there. So here we are considering two cases. One is before the engine fires, that means before rocket starts, and during the rocket firing. So simple diagram is there here. So it is fuel. The major part of the rocket is, or major mass of the rocket is from the fuel only, and this is the engine. Before engine fires, okay, before rocket starts. Let's take our system as rocket plus fuel. Okay, only we are considering here as rocket and fuel system. Suppose that the rocket is at rest somewhere in space. Okay? Initially we are taking the condition of rocket is at rest, where no outside forces will exert impulse on system. Okay, there is no other external forces. That's why this rocket we call it as isolated system. The law of conservation of momentum applies. Since both the rocket and the fuels are rest, their individual momentum are zero and the total momentum of the system is zero. Okay, now I am going to explain this paragraph. Consider an object here. Okay, here one more object is there. It has mass m and it has velocity v. Now its momentum is given by mv. Okay, and this one more object is there. It has mass m1 and velocity v1, and its momentum is m1 v1. The total momentum is sum of these two momentum. So that is total momentum is m1 v1, sorry, mv plus m1 v1. This is the total momentum if you consider this as an isolated system. Throughout the process or throughout the motion, the mass of these two objects is remains same. Okay, there is no change in the mass. Okay. Now I am considering one object. Its mass is m and velocity is v. Okay, momentum is mv. So now it is moving. It has momentum mv. During the motion, if this object loses its mass, okay, assume that, okay, it's not a case here, assume that its mass is decreases. Okay, so that is by m minus delta m. What is minus delta m? Some amount of the mass is losing, for that we are taking minus of delta m. Then what would be the velocity here? The velocity is here not v, because according to law of conservation momentum, the momentum is remains constant. Now if you take this as m minus delta m into v, these two factors are not equal. To maintain constant, if one term is or one variable is decreases, another should be increases. Here mass is decreases. To maintain a constant momentum, the velocity now should be increases. Then it becomes v plus delta v. Okay, so this is the case of conservation of momentum in variable masses. If velocity decreases, mass should be increases. It is not possible. If mass is decreases, the velocity may be increases. That is in the case of rocket. Now comes here. This is an isolated system. Before starting the rocket, the momentum is taken as 0 because the velocity is 0. Okay. Now its momentum is 0. Now here momentum I am considering two. One is rocket momentum, another one is fuel momentum. Okay, both are at rest with respect to one another. With respect to rocket, fuel is rest. With respect to fuel, rocket is at rest. The momentum of fuel is 0 and rocket is also 0. The total momentum is 0. Whatever happens, the total momentum should be 0 only, because according to law of conservation, during the action or during the process, the momentum not be varying, it is 0. So this is we are using in rocket system. When the rocket's engine fires, it pushes fuel out of end of the rocket. Suddenly part of the fuel has momentum mv towards the left. Now here in second diagram, when rocket starts firing, the fuel burns and then it exhausts through the outlet valve. Okay, here in this direction it starts exhausting the gases. Fuel burns means some amount of fuel is exhausted through this valve and the mass of the rocket is decreases now. Since the total momentum of the system was 0, total momentum of the system was 0 before the rocket fired, it must still be 0. This means the rocket must have an equal amount of momentum to the right. What happens now when fuel starts exhausted through outlet valve? It has certain velocity, so that take it as v, and the mass of the exhaust valve may be mass of the fuel exhausted through the exhaust valve may be delta m. Then its momentum is delta m into v. Okay, that means the exhaust gas has a momentum. If it has momentum, that means to maintain a constant momentum that is equal to 0, the rocket should also have the same amount of momentum. If it has same amount of momentum, then the direction should be opposite. Then only those two get cancelled. The total momentum now becomes 0. Okay? It should have the opposite momentum. For that, the rocket momentum is equal to minus of fuel momentum. The negative sign indicates two momentum vectors are in opposite directions, therefore cancel. When the momentum of the rocket and the momentum of the fuels are the same size, their velocities are not same. Since the fuel has a small mass, it gets a larger velocity. Since the rocket has larger mass, it gets a smaller velocity. Okay, as I explained here, to maintain a constant momentum, if one variable decreases, another variable should be increases. Here the amount of or mass of the fuel exhausted is less. Okay, fuel mass is less than rocket. Okay, rocket plus fuel, but this exhausted gas have higher velocity than the rocket. Okay, so that these two balances. Okay, in simple case, according to law of conservation of momentum, whatever the momentum of exhaust gas is there, so that is equal to the momentum of the rocket plus the remaining fuel in the rocket, but those two in the opposite directions. Okay, this is all about the linear momentum in case of variable masses. In next class, I am going to derive an expression, an important expression for equation of motion of rocket. Okay, so that is considering on the basis of law of conservation of momentum under variable masses. Thank you.